Well, good afternoon, everyone. It's the top of the hour here, so we will go ahead and get started. Thanks for joining. My name is Diane Lechner. I'm the VP of Sales here at Midland Scientific, and we're excited to have Hach joining us for a webinar today. A little bit about the presenter. Tim Ayer is the Global Product Manager for Hach. He has worked there for the past 9 years, based out of their Loveland, Colorado site. In this role, he focuses on delivering new solutions to customers and supporting customers with existing products from Hach. So Tim is going to lead the presentation today. I see that everyone is muted. If you could please remain that way. If you have questions, please feel free to put those into the chat box, and we will have some time for questions at the end as well. So with that, I will hand it over to Tim.
Thank you very much. Hi, everybody. My name is Tim Ayer. Thank you for the introduction. I would first like to say thank you, everybody, for your time today. Really great to see interest in our new products and where we're trying to help you in your facilities make your lives easier. Also, thank you to our partners and peers at Midland Scientific. For those of you who may not be aware, Hach and Midland, we do partner together to make sure that our solutions are available to you all. So we sincerely appreciate the opportunity to get in front of you as direct Midland Scientific customers. So appreciate the chance to get in front of you here, and thank you very much. So to set the stage, we are here to talk about first an application that I hope many of you are familiar with in terms of reverse osmosis membranes and operating and protecting that significant investment that perhaps some of you are already concerned with, or some of you may be considering in terms of bringing reverse osmosis membranes into your facilities to help you with your water processes. We'll dive into that a little bit, then we'll get into the specifics about new technology that Hach has brought to the market, and then a bit more specifically some features and benefits about that product. Again, please ask any and all questions you have. If I don't know the answers, we'll be sure to get them to you. I won't hesitate to tell you if I know the true answers or not. So please ask whatever comes to mind, and we'll be sure to follow up with any answers to questions we aren't able to answer here later on through Midland and our partners there. So diving in. When we think about reverse osmosis membranes, there are, of course, a number of different things in general that we need to be conscientious of when it comes to owning, operating, and maintaining reverse osmosis membranes. We at Hach, as you may well know, we dabble in a lot of different tests, in a lot of different applications, and we have many tests that cover a whole gambit of parameters. However, in the case of reverse osmosis membranes, where we really saw an opportunity to take our expertise and apply it here was specifically in chlorine and sulfite. Now, for those of you who are familiar with RO membranes, and you perhaps already operate those in your facilities, you are likely very well aware that depending on the type of reverse osmosis membrane you have or are considering operating, you need to be very mindful of oxidants. And here in North America, our primary oxidant that we have to deal with is chlorine. Many reverse osmosis membranes are sensitive to chlorine at one level or another. Some are capable of being hit, if you will, by higher amounts of chlorine than others. Some really need to have as little as possible in terms of chlorine that's allowed to make contact with the membranes. So that poses one challenge. We need to remove oxidants from our processed water, our feed water going into our reverse osmosis membranes. The counter to that, though, is when we remove oxidants and we remove any disinfectant residual, we leave our reverse osmosis membranes vulnerable to bacterial growth. We leave them vulnerable to what we refer to typically as biofouling. And that is also a potential problem, leads to reduced pass-through of our membranes, leads to maintenance requirements, and is something that we need to be mindful of. It can eventually destroy our membranes, if not at least cause us a hassle in terms of shutting down our RO skid or our whatever form your reverse osmosis membranes exist in your facilities. They may need to be taken down for maintenance or possibly replacement. So there's two stances you could take with your RO membranes, really, perhaps more. But the status quo, what we see most typically, is that we are willing to deal with biofouling with the assurance that we don't completely destroy our RO membranes by allowing too much chlorine to pass through those. There's certainly nothing wrong with that. Knowing in the real world that we can only do so many things perfectly, or we can only focus on so many things at one time, that perhaps is really the lesser of two evils. There is the alternative of really concentrating on dialing in that oxidant feed, dialing in that chlorine so that we allow a safe amount of chlorine to pass through our membranes. That can serve as a disinfectant and a check on biofouling potential. But that is, of course, much more difficult to do. But in either case, what is important when we're operating our RO membranes is that we have good tools to ensure that our dechlorination processes are running efficiently and that we are removing that really critical oxidant from we're either removing or controlling the level of oxidant that goes through our membranes. So this is likely a schematic that in one way, shape, or form everyone has seen. This is just a very general illustration of a typical water cycle in any given facility that has feed water coming in, typically through, of course, like a municipal supply, a city supply, comes into our plant, and we put it through some process, one or the other, depending on what we need to do. In this case, we are taking in feed water that hits a number of pre-filtration stages. It has a number of different parameters that are important across the water cycle. And at some point in time, because this pretend feed water is chlorinated, we put it through a dechlorination process. After dechlorination, you would typically want to understand the quality of that water that's feeding into your RO membranes. And so we would typically measure, you can see after stages 5 and 6, 6 being where dechlorination happens, we would monitor perhaps chlorine, pH is important, of course. If we didn't have a chlorine analyzer in place, maybe we're using ORP as a proxy measurement to gauge where our oxidant levels are. But I just wanted to show, where we would typically recommend that these type of measurements take place. So after dechlorination is really what we're talking about focusing on with this solution here. So for those of us who've been in the industry for at least a little while and might be concerned with protecting your RO membranes from too much oxidation breakthrough, you may be well aware that monitoring chlorine at ultra low range levels can be difficult. To clarify, when I say ultra low range chlorine, we're typically talking about chlorine below 100 parts per billion or 0.01 milligrams per liter part per million. Chlorine in itself is a very good oxidant, and it dissipates very quickly. So that is in essence part of the reason why it's so difficult to monitor at ultra low range levels. It's difficult to detect, it's difficult to create stability in our testing environment, and those common solutions that we're used to, sort of the tried and true methods for chlorine monitoring, are very good at what they do in the range that they're intended for. However, when we start trying to push those limits of what they're intended for and measuring either higher or lower, then we really need to be aware of the limitations of existing technology. Now, DPD is a traditional colorimetric type method that has been in the market for decades. Hach is just one of many manufacturers of DPD chlorine tests who have been manufacturing this chemical reagent for a long time. And it's done an amazing job for what it's intended to do, which is to monitor chlorine in sort of that standard low range. So we're talking about 20 part per billion to 200 part per billion, or 0.02 milligram per liter to 2.0. This has really been designed for drinking water type applications where we want and expect to see a residual of chlorine present in the water. But when we start trying to push DPD into these ultra low range levels, it's really where we're starting to get into sort of tricky waters. Anytime we talk about pushing a method past its designed capability, then we really need to be aware of the fact that at those far ends of our testing range, accuracy and precision inevitably becomes more and more strained and more difficult to have a lot of confidence in. Any standard bell curve would tell you that accuracy and precision is best in the middle of that working range, and it does tend to taper off at those tail ends. So in the case of existing DPD colorimetric methods or very difficult amperometric titration methods, so using automated titrators or titrators in general, those can be inherently difficult to operate. It becomes just simply difficult to measure ultra low range chlorine and really have confidence that we have operated a dechlorination process that has removed the amount of chlorine that we expected to and we've tuned it to. So you may employ a standard DPD test to verify that your dechlorination solution, or sorry, your dechlorination process has been effective. But if your goal is to have zero chlorine after dechlorination, you need to be aware that the DPD test you're running may only go down to 20 parts per billion. And at that level, we're at the low end of our detection range. And so how accurate is that 20 part per billion test? You may unintentionally be allowing 20 or 30 or 40 part per billion to be passing through your dechlorination process and into your RO membranes, which inherently reduces the lifespan of your RO membranes and potentially leads to premature failure. So I did somewhat gloss over those common dechlorination methods, so I might just backtrack a moment. Depending on the type of facility that you're operating, you may elect to use one of two common forms of dechlorination. So you may operate a granular activated carbon bed, which just simply uses activated charcoal and allows, it's a physical means of dechlorination. So we have our granular activated carbon in some sort of tank or system, and we push our feed water through that, and that charcoal grabs that chlorine right from the feed water, removes it through those physical means. And it's a great way to not have to pay for additional chemicals. It's a great way to make sure that we don't have additional chemicals after dechlorination to deal with downstream. And it is typically a reliable method as long as we make sure that we monitor the health of those granular activated charcoal beds, that we make sure we don't have any streams the terms escaping my mind. We don't have any channeling happening in those GAC beds. It is typically reliable and has its positives in terms of no chemical costs, easy to typically to maintain, and no additional chemicals after dechlorination to deal with. The other method is, of course, using a chemical means of dechlorination, in which case sodium bisulfite is typically the most common reductant agent that we would see being used to add to the feed water to remove chlorine through chemical means. Anytime we add a new chemical in our process, we need a means to control it, and we need to understand exactly how much we're adding, how much we're seeing come out at the end of our process, in order to control costs, in order to control downstream processes where you might need to remove that. And so in the case of feeding sodium bisulfite for dechlorination purposes, I should say, it has historically been very difficult to measure sulfite with any sort of real true accuracy. You could argue that by using a chlorine monitoring tool or ORP, you can use those as a proxy for measuring sodium bisulfite or sulfite. And you can understand that, well, if I know I have no chlorine in the system, but I maintain a small sulfite residual, then I'm okay with allowing that sulfite through. Sulfite is typically recognized as being cheap in our industry. And so you're content to just roll with that sort of process. And there's nothing necessarily wrong with that. I would not pretend to be an expert in your business and your processes. But what I do know is that although sulfite is relatively cheap and does not have direct harmful effects to our RO membranes, what is known is that sulfite is a chemical that can cause additional biofouling within our membranes. So we can have sulfite reducing bacteria proliferate in our RO membranes and clog those up even faster. We also know that sulfite can cause changes in pH. It is generally an oxygen scavenger used in the boiler sort of matrix. Serves its purpose well there, but within RO membranes, it can lead to a host of other problems. So in a market where sulfite has historically been difficult to test for, you either had the option of sort of standard color wheel test kits or a sulfite test kit in one way, shape, or form. You really had a lot of guessing. That was your best option. You could either use a proxy measurement, like a chlorine monitoring tool, and you just sort of roll with it. But we saw a need here at Hach to add a legitimate, highly accurate, highly precise sulfite measurement to the market for this purpose. And so we have recently launched the new DR1300 FL portable fluorometer that brings ultra low range capable methods in a portable, simple, easy to perform test method to your facilities. We can test for total chlorine, free chlorine, and sulfite using this new fluorescence technology that we'll talk about a bit more here. So how does fluorescence technology work? Fluorescence is not in itself new to our world and to our industries. Fluorometers have been in existence for quite a long time, and fluorescence has been measured or has been used to measure multiple different parameters for quite some time. So we think of PTSA in the power industry, or we think about oil and water in the wastewater industry, or we think about algae, certain algae. What's fluorescence in those cases is a form of fluorescence that's natural. So PTSA, oil and water, algae, they naturally emit fluorescence, and there's nothing wrong with that. I'm just bringing this up to draw a distinction between the fluorescence that we're used to in the market versus the fluorescence that we're offering in these new fluorescence tests using the DR1300 FL. When we think about fluorescence in general and what's special about it, there's really one core important factor about fluorescence that has really made sort of this new revolution in ultra low range testing possible, and that is stability. So I have this little distilled way of thinking about what is difference about fluorescent versus the traditional colorimetric tests that we're used to seeing. And I hope that hits home, because one of the amazing parts about fluorescence is this ability to create a stable sample matrix and stabilize these analytes that have historically been very difficult to stabilize. I do have a video that will link to sort of exemplify how fluorescence works, but for now, I'll jump in and explain it a little bit more. So when we analyze fluorescence, what we have observed in our Hach R&D facilities is that fluorescence in general is more stable than absorption. And when I say absorption, I'm referring to color absorption that we are typically analyzing in our colorimetric methods done on portable colorimeters or benchtop spectrophotometers. When our indicator reagent, so in our total chlorine test and free chlorine test and sulfite fluorescence tests, they're comprised of a two reagent system. You have an indicator reagent and a buffer reagent. In every test, we add a specific indicator through the use of just a simple dropper bottle. We add 5 drops of our indicator to the reagent, and when that's added, it seeks out that analyte, that free chlorine, total chlorine, or sulfite, and it bonds and creates what's referred to as an active reporting fluorescent molecule. Now, a fluorometer is really nothing all that complicated. It's very similar to a colorimeter in that we have a light source that emits a specific wavelength of light, and then we detect on the other end of our sample. And so in this case, the DR1300 FL, its light source, its LED, activates that fluorescent reporter molecule, that active reporting molecule, and that molecule then emits fluorescence. So again, going back to fluorescence in the previous times, those molecules that naturally fluoresce, they give off their fluorescence themselves. Here we're actually creating fluorescence. And so we've added our indicator reagent, we've created this molecule, we excite that molecule, it gives off fluorescence, and then the DR1300 FL detects that fluorescence that's created, and based on its internal calibration curve, it equates that to a concentration of the analyte for you. That active reporting fluorescent molecule has been shown to be incredibly stable, and that is what allows us to analyze things like chlorine, which change very quickly, especially at ultra low range concentrations, with high accuracy and precision. So really if you're familiar with colorimetric tests, for instance, you've grabbed a sample, you've added it to your sample cell, you've cracked open a powder pillow from Hach or some other provider of DPD, and you add it to your sample, and you have to wait a given amount of time. And you measure at 2 minutes, let's say, and then out of curiosity, you measure again a minute later, and again a minute later, and again a minute later. And every time your reading just goes up and up and up. And you wonder, well, how do I know what's right? And at Hach, I'm sure some of our competitors, we would advise you to measure at that specific time after the reaction has been completed. And that's because that is where the peak color development has happened and the most accurate concentration can be gathered. What we've seen with our active reporter molecule is that it stops chlorine from changing. It creates this stable molecule, which we can then translate into an actual concentration. And this is the primary reason why we're able to go to single-digit part per billion levels with chlorine and sulfite with high accuracy and precision, better than we ever have been able to before. So just a bit more about the instrument. We are talking about total chlorine tests that can go from 3 to 100 part per billion, a free chlorine test that can go from 2 to 100 part per billion, and a sulfite test that can go from 6 to 500 part per billion. You can see there that at 50 part per billion in our chlorine tests, we have a precision of plus or minus 1 part per billion. So should you be testing in that range of 50 part per billion chlorine, you can expect the accuracy of your results to be between 49 and 51 part per billion. Sulfite, we have a little bit more. However, that needs to be not quite as precise as chlorine in this case. These test results can be obtained using very easy to perform tests. So I would argue one step more complicated than a traditional powder pillow test. We are taking a small amount of sample, we're putting it in a somewhat standard test tube, and we are adding, using 2 dropper bottles, 5 drops of each reagent. In the case of chlorine, we are in total chlorine, we're waiting 2 minutes after the reagents have been added until we test for the result. Free chlorine, the results are instant. And in sulfite, we have a 15-minute reaction period that we're waiting after reagents are added before reading for the analysis. And so these new tests are easy to use, an instrument that is very intuitive and simple to navigate. One nice thing about these reagents is they're a bit more environmentally friendly than tests of the past, in that the reagents themselves are less toxic and we use less of them in general. So there's less of an environmental footprint through using these tests. And these tests can help you in reducing chlorination, dechlorination costs, reducing maintenance requirements of your RO membranes, and ideally help you prevent that really almost doomsday scenario of that RO membrane is 6 months old, and all of a sudden we let too much chlorine go through, and it's burned and it needs a full replacement that's out of warranty. So with that, I think that concludes my presentation, Diane. I'm happy to take questions and talk about anything you're interested to know.
Thank you, Tim. So if anyone has any questions and they would like to unmute and ask those, they certainly can right now. I did have a couple come in here, so I'll kick it off with those ones. One of them said, how long does it take to run these tests?
Perfect. So again, the total chlorine, when we think about gathering our sample, adding it to our test tube, addition of reagents and required reaction times, the total chlorine test might take 5 minutes to perform. Free chlorine test, arguably less, considering there's no reaction time, so we'll call that 3 minutes. In the sulfite test, from start to finish, grabbing your sample, adding it to your cells, addition of reagents, and then reaction time, we're probably looking at anywhere from 16 to 17 minutes.
Okay, and then the other one was, which parameters is Hach coming out with next?
So we do have a pipeline of parameters that we're investigating. So we really have our eye on those parameters that we typically need precise ultra low range information on. We have a number in development right now, but it's a little too early to come out and say we're developing, only because I'd hate to make promises we can't keep yet. But that is one of the exciting things about Hach diving into a new form of technology, is that we're really curious to see where else we could take this and either produce greener tests or tests that are better for you in applications you need them in.
Sounds good. And I was just curious, are these reagents hazardous for shipping?
So the most hazardous component in our all of our chemistries is isopropyl alcohol. So we do have to have transportation hazard codes because of isopropyl alcohol. They don't typically want those on airplanes for too long. They don't typically want them in high quantities. We are talking about small amounts of isopropyl alcohol. Outside of that, there is very low toxicity to humans with regard to all of these reagents and all of these tests that we have.
Okay, well, if there is no other questions here for everyone on the phone, we will be sending out the presentation via email, and that will include the videos that Tim mentioned. And if you have any questions, don't hesitate to reach out, and really appreciate your time today. Thank you very much, Tim.
Thank you. Pleasure to be here. Thanks everybody for your time. Please let us know if you have any questions. Have a great day.